Hi students, welcome to today's lecture on artificial neural networks. So in our previous sessions on unit 4, we have discussed about what are multi-layer feed-forward neural networks. And then we have gone through the steps used in backpropagation algorithm in our previous class. Today, we'll see a solid example of applying this backpropagation algorithm and see how this algorithm can be used to train our neural network uh, with the help of an example, a solved example. Okay, so we'll see the steps involved in backpropagation algorithm one by one to solve a particular problem selected. Okay, so let us start with a simple introduction to the backpropagation algorithm. Okay, so what is a backpropagation? We know that backpropagation is a supervised learning algorithm for training neural networks, particularly for feed-forward neural networks. Imagine, observe this diagram. There is one input layer, one hidden layer, and one output layer. Okay. The connections are always from input layer to the output layer. Okay, so the connections are always in forward direction. The flow of information will be in forward direction only. Okay, so this is a feed forward neural network. Therefore, the backpropagation algorithm can be used to train this feed forward neural network. Right. So this we discussed in our previous class also. Then why we actually need this backpropagation? So you need to understand this point why you actually require this backpropagation. Let us imagine a neural network as a general neural network, something like this, in which we have two neurons in input layer and two neurons in hidden layer and one neuron in output layer. And we all know that initially the weights are uh, initialized to some random values, that is W1, W2, W3, W4, and W5, W6 would be initialized to some random values at the beginning, generally between 0 and 1. Okay, and then once we supply a particular input pattern I1 and I2, and because the model knows what is the target value, okay, so the target value will be uh, fed to this model. Once the inputs are given, because the model knows the target, it calculates the actual output produced here. Okay, this is the actual output produced by the model, that is the predicted value produced by the model. Uh, then we need to compare this target and actual. So generally, in most of the scenarios, because these weights are initialized to random values, it's not possible to get the target value directly with these initialized weights. Okay, so therefore, there may be some error produced, and based on the error produced, we will update these weights and so on until the model properly predicts the corresponding target output for a given input pattern. This is what happens. Okay, so for doing so, we require the backpropagation algorithm. Okay, so let us see how this happens with the help of a simple scenario. Imagine that inputs are given as 2 and 3, and imagine that the initial weights are given as 0.11, 0.21, 0.12, 0.08, and these two are 0.14 and 0.15. Okay, so after calculating the value produced by this hidden neuron, it is 0.85, and this is going to be 0.45, and these comes as inputs to the output layer. And then we calculate the output of this uh, output neuron, which is going to be 0.191. Okay, you can see that it is 0.191. And imagine that the actual output is 1. Okay, so you can see 0.191 is very far from this actual output one. Okay, this we will compare these two, and we will calculate the error term by using a formula, mean square error, half into prediction minus actual whole square. Okay, so prediction is 0.191, the actual is 1. Okay, so the error is 0.327. Okay, so this error is produced. We will try to minimize this error by updating the weights of the neural network connected over here. So for updation of these weights, we need this backpropagation algorithm. Okay, so that is why we need this backpropagation algorithm. That is the answer for why we need backpropagation. Right? We need to understand how the backpropagation updates the weights. Either the weight may be increased or maybe decreased also. So let us imagine that this is the square error. Okay, and then to achieve this global minimum, always remember that backpropagation targets to reach this global minimum. Okay, so the global minimum is here. So for reaching this, either you may be increasing the weight or you may be decreasing the weight. Okay, so based on what is required, we will calculate that. We will make use of gradient descent to find that global minimum loss of a error function. Global minimum loss of a error function. Okay. Generally, the target of gradient descent will be to minimize the given error function, and weights will be updated accordingly to minimize that error function. So always we move towards minimizing the error function quickly with the help of gradient descent. We'll see how it can be done with the backpropagation algorithm. Let us summarize the steps that we discussed in our previous session as part of the backpropagation algorithm. These are the steps generally. Assume that this is the model we are building. Okay, so it is already built with some random weights. Okay, now we will calculate the error based on the model built till now. Okay, if the error is minimum, that is satisfactory, then we say that model is ready to make predictions. Otherwise, we update the parameters by using the gradient descent operation model or backpropagation, let us say. Okay, and again, these updated parameters will be given back to the model to calculate the error. Okay, so this process, calculation of error, checking whether error is minimum or not, updating the parameters, this process is repeated a number of times until the error becomes a satisfactory for the corresponding model. Okay, so this process of doing repeatedly calculating the error and updating the parameters is called as training process. Training process of the neural network is actually named with this calculation of error and updating the parameters repeatedly. Okay, so once the model is ready, we can use that model for making some predictions for the given set of input patterns. So this is what we discussed in our previous class. Okay, so let's go through that video also to understand it properly. This is just a summarization of what we discussed as well. Now, to understand our backpropagation algorithm, imagine simple feed-forward neural network, something like this, in which we have three layers. One is input layer with two neurons I1 and I2. One hidden layer with two neurons H1 and H2. O1 and O2 are output neurons in output layer. Okay, and the weights connecting the input neuron I1 with H1 is W1, I1 with H2 is W3, and I2 with H1 is W2, I2 with H2 is W4, and there is a bias also connected to these H1 and H2 in hidden layer. Okay, so the bias weight is B1. And we know that the input for bias weight is always going to be positive one here. Okay, similarly, H1 to O1 is connected through the weight W5, and H1 to O2 is connected with W7. H2 to O1 is connected with W6, H2 to O2 is connected with W8. and there is a bias also connected to the output neurons B2. And here also the input value for the bias weight is always 1. Every bias weight is connected with first one only. So B2 is connected to O1 and O2 here, along with the weights. Okay, so this is the scenario I am assuming. And now let us take a sample input and the corresponding target outputs for this neural network, a sample neural network, and then with some initialized random weights, we will try to uh, design this back propagation neural network. So here is the sample data we are assuming for understanding our back propagation algorithm steps. Uh, Let us say the inputs I am giving is 0.05 and 0.10. Okay, and for this input, the output must be 0.01 and 0.9. That means whenever I give this input 0.05, 0.10, they should produce 0.01 and 0.99 at the output layer. Okay, so the size of input pattern is 2 and the size of output pattern is also 2. Okay, and for connecting, I'm taking some random values here. W1 is 0.15, W2 is 0.25, W3 is 0.20. W3 is, okay, this is W2. W2 is 0.20, W3 is 0.25, and W4 is 0.30. Similarly, W5 is 0.40, W6 is 0.45, W7 is 0.75, W7 is 0.5, and W8 is 0.55. Similarly, I am assuming the bias 1 as 0.35 and bias 2 as 0.60. These are all random values. We did not get these values. They are initialized randomly to some values over here. Okay. Can go with any other values also. It's not compulsory that you should follow these values. Okay. And this is the input pattern that we are considering. I1 is equal to 0.05 and I2 is equal to 0.10. And the neural network should produce these outputs whenever I submit this input pattern. Okay. So these are target values. Now let us see whether these weights which we took at initial configuration are producing the target outputs whenever I submit this. Okay, if they produce the target outputs directly, then it means your model is ready to uh, use for predictions. Otherwise, you need to update these weights by using the backpropagation algorithm. Okay, now let us see how it can be done. So we all know that backpropagation algorithm uses two passes. One is forward pass, which calculates the actual outputs produced by your neural network, and the backward pass, based on whether the error is satisfactory or not. The backward pass updates all the weights connected to the neural network. Okay, let us see each pass now. Okay, we begin with the forward pass, the first step. In forward pass, what we do is we try to calculate the output of O1 and output of O2. In order to calculate the outputs of O1 and O2, first we need to calculate output of H1 and H2 because these are connected to the output neuron. So we'll start with this first. We'll try to calculate the output of H1. For that, what we need to do is first we need to calculate net H1, which is using the formula W1 into I1 because this is connecting over here, W1 into I1, and this one W2 into I2. Okay, because these two are connecting H1, we will take W1 into I1, W2 into I2, this one, plus a bias is also connected. Okay, so by using these three, we will calculate the net H1. The formula is W1 into I1 plus W2 into I2 plus bias 1. Okay, and substitute the values, we will get 0.3775 as net H1. So this is net H1 before it is passed on to the activation function. So the Output from H1, that is out H1, is calculated by sending this net H1 to some sigmoidal function. Okay, so out H1 is calculated as 1 by 1 plus e power minus net H1. That is, this value is given to the sigmoidal function. Okay, then it comes as 1 by 1 plus e power minus 0.3775. You can calculate this as 0.5932, something like this. Okay, use that calculator to calculate this value. Okay, we require some advanced calculators while doing this mathematics. Okay, you cannot do it manually. Right? So similarly, we can calculate the output of H2 also. So what is the output produced from this H1 now? It is 0.59. Okay, so the output produced by this H1 is calculated as 0.59. Similarly, you can calculate the output of H2, right, by using the same formula. First, you need to calculate net H2. So what is the formula for net H2? Can you write down that formula for net H2, right? What is the formula for net H2? It is going to be, because net H2 is connected with W3 and W4, it becomes W3 into I1 plus W4 into I2 plus B1, right? I repeat, W3 into I1 plus W4 into I2 plus B1. That is the formula for net H2. Okay, and then whatever value you get for this net H2, you just pass it to the sigmoidal function just like this, and out H2 will be calculated with 1 by 1 plus e power. What is the formula for out H2? 1 by 1 plus e power minus net H2 that we calculated in this step. Okay, minus net H2. That is the formula for calculating out H2. So we got 0.59 here. Again, it is 0.596. So H2 value is also, this is 593 and this is 0.596. We got these values as outputs from H1 and H2. Okay, so now we use the same process to calculate out O1 and out O2 also. Okay, so for this, the inputs are 0.593 here from H1 connecting to O1 and O2. Okay, and connecting to H2 is connected to O1 and O2, 0.596. Okay, so how do you calculate net O1 now? The formula is W5 into 0.593 plus W6 into 0.596. That is net O1. Similarly, net O2 will be calculated as W7 into 0.593 plus W8 into 0.596 plus bias 2. It is common for both the output neurons. Okay, now let us see how these are calculated and what will be the values produced by O1 and O2. Okay, so we use the same process for calculating net O1, but this time for calculating net O1, we use out H1 into W5. So whatever out with H1 we got, it will be multiplied with W5 plus out H2 into W6. That is the formula. Okay, so out H1, W5 into out H1 plus W6 into out H2. That means the outputs produced by the hidden layer will act as inputs to the output layer. That is what you need to understand. Plus bias 2 is that. Okay, so when we calculate this, net O1 becomes 1.10590, something like this. And finally, because this is net O1, the final output of this neuron will be calculated by sending this value to the sigmoidal function. Therefore, out O1 is equals to 1 by 1 plus e power minus net O1. Okay, so 1 by 1 plus e power minus 1.1059, which will become 0.75. So the output produced over here is 0.75. Okay. Similarly, we will use the process to calculate the output of O2. Okay, out O2. So we need to calculate net O2. What is the formula for net O2? Net O2 formula is W7 into out H1 plus W8 into out H2 plus bias 2. That will be the formula. Okay, by using this formula, we will calculate the output of O2 also, which will be 0.7729. Okay, so this is producing 0.75 and this is producing 0.7729. As you can see, the expected value is 0.1, but the produced value is, okay, you can compare these two. The produced value of the neural network is 0.75, which is very far from the actual output expected. So 0.75 is very far from 0.01. So we need to update the weights. Okay. Similarly, here we are expecting 0.99, but the output produced by our neural network is 0.77. So we need to update the weights in order to get the target outputs 0.01 and 0.9. So there is some error in the neural network. So we require updation of weight parameters, right? Now let us see how it can be calculated. We need to calculate the error term first, and then using that error term, we will update the weights of the neural network later. So how do we calculate the total error? So we saw it in the previous class. The algorithm specifies you are going to use some mean square error. E total is equals to summation of half into target minus output whole square for every output neuron. Therefore, EO1 is calculated as half into target O1 minus out O1 whole square, which becomes 0.274. So this is the error produced by output neuron O1. Similarly, for EO2, what is the formula? Half into target O2 minus out O2 whole square. Okay, target O2. What is target O2 here? It is 0.99 minus out O2 is 0.77. What is it? 0.77. Okay, so 0.99 minus 0.77 whole square. Right. So the total error is sum of these two, the error produced by output neuron O1 error plus error produced by output neuron O2. EO1 plus EO2, that gives us 0.29. So this is the total error caused by your neural network, right? So with the help of this error, we will try to propagate this error to update all the weights of neural network like this. So we start with the output layer and we propagate the error to the weights of this connections between hidden layer to output layer, and then we use the error propagation to the connections of input layer to hidden layer also. Okay, so let us start this updation of error propagation. Okay. Right. So how do we do this? For that, we require the backward pass. So the second pass is backward pass. Okay, so as explained. In backward pass, what we do is we will update the weights using gradient descent. Okay, here we are going to make use of gradient descent. That makes use of that derivatives of the error terms, and we'll propagate that derivatives of error terms to the actual weights connected in the neural network, and we will update them accordingly. Okay, so the ultimate goal of using this gradient descent is to quickly move towards error minimization. Okay, so see how this gradient descent can be used now to quickly move towards the error terms. So let us start with the first step. We'll start with the connection between hidden layer and output layer. So let us consider W5. Okay, W5. We need to see where it is actually. So this is where I want to update this W5 now, which is connecting H1 to O1. I want to update this W5. So what I will do is to update W5, just look at this. Okay. To update W5, what you need to calculate is you need to calculate this dou E total by dou W5. Okay. So this will give us the partial derivative of E total with respect to W5. That will be used for updating the weight W5. Okay, that means we are propagating the error term to update the weight W5. Right. So how this will be calculated? To calculate this, we need to use this formula. How it came? Look into this diagram now to understand this formula. It is very easy. Okay. Uh, this is the output neuron 1. Okay, so output neuron 1, O1. This is O1. We know the values of net O1 and out O1 also. And we know the E total, which is calculated as EO1 plus EO2. Okay, so then the formula will be dou E total by, see this, dou out O1. This is where you will start. Dou E total by dou out O1, the first term, into, then we will start from here to here. Dou out O1 by dou net O1, that will become the second term in the multiplication, into, and here to the corresponding weight which you are updating. Because we want to update W5, it is going to be dou net O1 by dou W5. That becomes your third term. You can easily write this formula. You can easily remember this formula to propagate backwards starting from the error term. So E total to out O1 to net O1 to W5. Similarly, if you want to update W6, you will go like this. E total to out O1 to net O1 to W6. Okay, so that is how you do, right? And depending on whether you require bias updations or if you fix the biases, then you don't require any bias updations. Okay, if you want to update bias also, then you need to use that formula. Generally biases will be fixed statically, so we don't require that. We will update only W5 and W6, right? So this is the formula. Once you are able to write this formula, then you need to understand how this will be calculated and how this will be calculated, the individual terms in this formula. You need to understand and how this will be calculated. So let us see one by one now. The first thing is, how do you calculate this dou E total by dou out O1? Dou E total by dou out O1 will be calculated as this. Look at this. Dou E total by dou out O1 will be calculated as applying the partial derivative on E total. What is E total? It is the error term O1 plus error term O2. Error term O1 is half into target O1 minus out O1 whole square plus half into target O2 minus out O2 whole square. So when you partial derivative with respect to out O1, okay, then this term becomes constant, okay, because it contains target O2 and out O2. So this becomes constant and becomes 0. Okay. And you need to apply this partial derivative over here. So how you will calculate the partial derivative on this? Then it is going to be 2 into, because we have whole square, 2 into half constant. So 2 into half into target O1 minus out O1, because it contains the term out O1, whole power 2 minus 1. Okay. Square minus 1 into, you apply this with respect to out O1, then you will get minus 1 here. This is going to be 0. Okay. So this is a simple derivation calculation, which becomes 1 into minus of target O1 minus out O1, or out O1 minus target O1. You can see this formula. So try to remember this formula. We will apply this every time. Okay, so dou E total by dou out O1 is going to be minus of target O1 minus out O1, or you can say out O1 minus target O1 directly, so which is becoming 0.74. So whenever you are calculating dou E total by dou out O1, you use this formula. Similarly, whenever you want to calculate dou E total by dou out O2, what will be the formula? Out O2 minus target O1. Target O2. Okay, and so on. You'll use the same formula every time when you try to calculate dou E total by dou out rho 1 or whatever it is. So it depends on this. Okay, depends on this. Right. So after calculating this, let us see how this will be calculated. Okay. All right. Dou out O1 by dou net O1 will be calculated like this. So we know that net O1 is calculated as W5 into out H1 plus W6 into out H2 plus bias. Now, dou net O1 by dou W5 is going to be 0.593. This we already calculated. Now, uh, let me see this. Actually, it is dou out O1 by dou net O1 is actually calculated with the formula, as it is a sigmoidal function. We can use the formula out O1 into 1 minus out O1. This will be the formula. This will be the formula for calculating this. Dou out O1 by dou net O1, and dou net O1 by dou W5 is going to be the coefficient of W5. Just go through that previous uh, video which I explained the steps used for calculating these two terms. Okay, dou out O1 by dou net O1 will be calculated as out O1 into 1 minus out O1. Okay, and dou net O1 by dou W5 is going to be coefficient of W5 in this net O1. So what is the coefficient of W5 in net O1? See, coefficient of W5 in net O1 is 0.5, right? So that is what we will make use of. So this is how the dou E total by dou W5 will be calculated after knowing all these three terms: dou E total by dou out O1, dou out O1 by dou out O1 by dou net O1, dou net O1 by dou W5. The final value of dou E total by dou W5 is 0.082167. Okay. So here is what actually I missed this slide. From here to there. Okay. So initially, by calculating this dou E total by dou out O1, we got this 0.74, and then this second term, dou out O1 by dou net O1, actually we know that out O1 is a sigmoidal function, which is to 1 by 1 plus e power minus net O1. So once we apply that derivation on this, we get f of x into 1 minus f of x if f of x is 1 by 1 plus e power minus x. We know this mathematically. I explained this in earlier class also. Therefore, since in place of x we have net O1 here, the formula is going to be uh, out O1 into 1 minus out O1. Okay, so in place of dou by dou net O1, we are deriving out O1 here. So the f of x is now out O1. Therefore, out O1 will be used as out O1 into 1 minus out O out O1 out O1 into 1 minus out O1 in place of dou out O1 by dou net O1. Just remember this formula. There is nothing to derive over here. So you just try to remember this formula whenever you have dou out O1 by dou net O1, because out O1 is a sigmoidal function. We are sending the value to some activation function, logistic function, which is derivable, differentiable. The formula goes like this: f dash of x is equals to f of x into 1 minus f of x. So in place of f of x, we have out O1. So we get this out O1 into 1 minus out O1. Just remember this formula. There is nothing complexity you need to remember over here. Okay, so this we calculated with respect to the derivation term in our previous slide, and this we can calculate using this formula, and this is simply going to be coefficient of W5 in network. Okay, so coefficient of W5, that is going to be 0.5. So this is how we get 0.0821 for W5. Once you got the value of W5, now we are ready to update the weight W5 by using the formula that I explained in previous class. W5 plus, that is updated weight W5, is equals to W5 minus eta into dou E total by dou W5. This we calculated in the previous step. Okay, so we already calculated this. We got it as 0.082. Therefore, the original weight of W5 is 0.4 minus eta is assumed as 0.5 at the beginning, and then it is multiplied with dou E total by dou W5. Final value of updated weight is 0.3589. So in place of 0.4, now it is 0.3589. Don't substitute it directly until you get all the weights updated. Okay, then only the neural network assumes these changed weights. Okay, now similarly, just like we applied for updating W5, use the same process to modify the weights W6, W7, W8 also. Okay, so if you use the same process which we did for W5, you will get the updated values of W6, W7, and W8. So use the same formulas with respect to W6. So in place of W5, you need to use W6, and in place of for W7 and W8, because they are connected to O2, in place of O1 you will be using O2. Okay, so this is how we calculate. So once we are updated W5, okay, so the actual updates must be done only after the complete neural network weights are updated. Don't use, for example, if at all you want to use W5 while calculating the updation for W1, you should use the old W5 value only. You should not use the updated value. Only once all the weights W1, W2, W3, W4, W5, W6, W7, W8 are updated and available, then only the network weights will be updated. Okay, so we'll continue with old weights only when we perform the remaining weight updations, right? So similarly, so once the output neurons weights are calculated, the 4 output weights are calculated, we have 4 more weights, W1, W2, W3, W4, which are connected to the hidden layer, right? So we'll try to update this now. And the formula goes like this. Suppose I want to update W1, dou E total by dou W1 is equals to, you will start with dou E total by dou out H1, it will be here, and then dou out H1 by, okay, so dou E total by dou out H1 here, and then dou out H1 by dou net H1, the second term, into dou net H1 by dou W1, the third term. Okay, so this is the formula we get, starting with the dou E total by dou out H1 into dou out H1 by dou net H1 into dou net H1 by dou W1. And for this hidden layer neurons, dou E total by dou out H1 is calculated as sum of all those error terms derived with respect to out H1. Okay, so it is going to be dou EO1 by dou out H1 plus dou EO2 by dou out H1. Individually, you need to calculate, right? So we know that EO1 is half into target O1 minus out O1 whole square, and out O1 is this formula, net O1 is this formula, and this dou EO1 by dou out H1 becomes dou EO1 by dou out O1 into dou out O1 by dou net O1 into dou net O1 by dou out H1. So we will reach from error term EO1 to this. Okay, so you can see this. Let me clear everything here. so that you will understand how this formula came. But this formula, because it is with respect to error term O1, you will start over here, EO1 with respect to out O1, the first one. Dou EO1 by dou out O1, and then dou out O1 to dou net O1, the second term, and then dou net O1 to dou out H1. Okay, from here to dou out H1, the corresponding output of this. Sorry, actually here it is. Let me clear this. I have not given it properly. Dou EO1 by dou out O1, and then dou out O1 by dou net O1, and this dou net O1 to dou out H1 from here to here. Error term O1 is corresponding to this only. Okay, so this is what we are calculating using the formula. Okay. Now let us calculate the actual value produced here by using the formula which we derived here. So dou EO1 by dou out H1 is equals to dou EO1 by dou net O1 into dou net O1 by dou out H1, which will be 0.05539. Similarly, dou EO2 by dou out H1 is going to be minus 0.01 by applying this formula. Okay, so the final value is going to be sum of these two, dou EO1 by dou out H1. So it is going to be 0.055 plus minus 0.01, which will give us 0.036. Okay, so once we calculate this, we are ready to calculate the actual value of dou E total by dou W1. So because we got this value, this is anyhow going to be out H1 into 1 minus out H1, and this is just going to be the coefficient of W1 in net H1. Okay, right? So let us calculate those two also. Dou out H1 by dou net H1 is going to be out H1 into 1 minus out H1. It's going to be 0.59 into 1 minus 0.59, which will give 0.24. And finally, dou net H1 by dou W1, that is the coefficient of W1 is going to be I1. Okay, so I1 is 0.05. You can see it here. So because we got all the three values in the multiplication, just multiply them. Dou E total by dou out H1, we calculated it as 0.03 into this is 0.241 into this is 0.05. So all the three values are multiplied here. The value we got is 0.004. That is dou E total by dou W1 we got. Okay. Now, so because we now got that value, we can update the weight W1 using the formula W1 minus eta into dou E total by dou W1. Okay, so the actual W1 is initialized at 0.15 minus, we know the learning rate eta is 0.5 into, we got this value dou E total by dou W1 as 0.004. Okay, so that is what we substituted here. So the final value of updated W1 is 0.149, something like this. Okay, so we'll apply the same process to update W2, W3, W4, the weights which are connected to the hidden layer further. Okay, so we get W2 plus, verify these weights after proceeding these calculations. So W2 plus should be 0.199 something, W3 plus should be 0.249 something, W4 plus should be 0.299 something like this. So we got all the weights updated now. Now let us calculate. So since all the weights are updated, now what we do, it's a repetition process. Again, we will go back to calculation of the outputs, and then we will check whether the error term is minimum or not. Otherwise, we will update the weights again using this process. Okay. So initially the weights 0.05 and 0.1 are supplied as inputs. The error on the network is 0.29. Now, if you apply this updated weights, the error term, if you calculate, it will become 0.291. It is something changed here, 0.298 to 0.291. Okay. If you repeat this process for 10,000 times, then the error may be reduced. So it is, you need to apply number of epochs for reducing the error function. Okay, so that is what I want to explain today. Please practice this problem properly to understand the steps of backpropagation algorithm. That's all for today. Thank you for your patient listening. See you again with another example in our next class. Thank you.